Okay, thank you very much. So let me start by joining all the other speakers in thanking the organizers for this wonderful workshop. I have been having a great time here. It's also my first time in Korea, and it's been very enjoyable. So many thanks for that. So yes, so I will be talking about fluid gravity, but with a twist. Normally, fluid gravity is studied from sort of using Einstein's theory of general relativity. But in this talk, I'll try to make the case that it might be more general than that, and you could actually use something we call non-relativistic gravity. So I'll define that later in the talk. But the talk actually is also aimed at sort of introducing you to some concepts that we've been playing around with for quite some time now that revolve around the idea of these non-Lorentzian geometries. And you have heard about this in some previous talks. So I'll start by talking a bit about non-Lorentzian geometry and why we believe that they're interesting, in particular for applications to fluid dynamics and condensed matter physics, but also many other areas. So a lot of the recent developments, and you can think about string theory, gravity, field theory, that don't have, for systems that don't really have Lorentz symmetry or approximations of systems with Lorentz symmetry, have been made over the recent years because we understand a lot better what replaces Lorentzian geometry. And so we coin these spaces non-Lorentzian spacetimes, and on the next slide I will be a little bit more precise about exactly how they are defined. Perhaps the most common and oldest example of a non-Lorentzian geometry, I mean, it's been around for more than 100 years, is Newton-Cartan geometry. So when Cartan was studying Einstein's theory in the 1920s, he realized that, in fact, you can also geometrize Newtonian gravity and write that in a covariant language. And in order to do that, you need to use something called Newton-Cartan geometry. And in fact, we'll see in some detail exactly what that is like. But there are many other non-Lorentzian geometries. There's nowadays a distinction between what we call type 1 and type 2 Newton-Cartan geometry. There's string versions of it that are relevant for string theory. I will not talk about that. And then there are Aristotelian geometries that have been mentioned already previously, and also Corollian geometries, which is a concept that is quite popular these days, and that has also been mentioned in some previous talks earlier this week. And they find applications in hydro, condensed matter physics, other theories of gravity like Rojava-Lifshitz gravity can be viewed in a diffeomorphism covariant way if you use Aristotelian geometry. There are various BF theories and Chern-Simons theories of gravity that use these geometric notions. Anything that is non-ADS holography is almost certainly going to bring you in contact with non-Lorentzian geometry. The reason for this is that ADS is special in many ways, but in one way, for example, because if you go to infinity, the boundary there is still Lorentzian. But that's actually very special, and normally that is not what happens. So for example, in flat space, if you go to infinity, you do not find a Lorentzian geometry, but you find this so-called Carroll geometry. So for example, all the radiation is collected at future null infinity. That's a null hypersurface, and therefore it doesn't have Lorentzian geometry, and it has this so-called Carroll geometry. And this is also true for various other non-ADS spacetimes. So if you believe in a non-ADS holography, then you will have to somehow become familiar with non-Lorentzian geometry, because there's more of the rule rather than the exception. So just to be a little bit more precise about what we mean by non-Lorentzian geometry. So as the word suggests, there is not a Lorentzian metric. In fact, there won't be in general an invertible metric on these spacetimes. So you may wonder, how do you proceed? And the simple answer is that you have to use Vielbeine. So you have a nowhere vanishing, everywhere invertible sort of complete set of Vielbeine, so that span the tangent space. But these Vielbeine do not transform into the Lorentz group. So we will collect the Vielbeine in this way. So tau will be like what you would normally call a time-like Vielbeine. And then the E's will all be all your spatial Vielbeine for for as many as you have spatial dimensions. And they will transform in some linear representation of some group G. And we will assume that there are spatial rotations. So there is some SOD subgroup that just transforms the E's among themselves on the rotations. So that is essentially, in a nutshell, what we mean by non-Lorentzian geometry. Typically, almost always, this is not the end of the story. There are additional fields, like you can think of them as gauge fields. We'll see later exactly what we mean by this. That also have these group G also acts on those fields. So this is what makes it a little bit more difficult to classify these spacetimes, because it's quite difficult to classify this particular aspect of them. But if we just focus on the field binder, there's essentially 3 different flavors for non-Lorentzian geometry. So there's the Newton-Cartan geometry, where the clock, we'll call this the clock 1 form. So this is what knows, if you integrate this along a curve, it tells you what the time difference is between 2 space-time events. So in Newton-Cartan geometry, that doesn't transform, but all the action is on the spatial field binder. So these are the rotations, but this is what we call a local Galilean boost. So these parameters, a lambda, are functions on space-time. So the spatial field binder going to the time-like field binder, but not the other way around. The other option is that you put this over here. So this is what Carroll geometry is. So now time is relative, if you like. So the time-like field binder going to the space-like field binder, but the space-like field binder only rotate among each other. So this is in some sense absolute notion of space, and this is an absolute notion of time. You can also take the intersection of these two, then you get Aristotelian geometry, where there are no boost symmetries at all. So you have absolute time and space. So essentially, this is all the options that there are. The only way that you can generalize this is that you can allow for more than one of these taus. So this is what happens in string theory. I will not talk about that, but just to mention for completeness, you can put an index, a Lorentz index, in fact, on tau, and then you get many stringy versions of this. Then if you want to proceed, you need a connection and curvatures and all that, and that follows from some field band postulates. And that all has been worked out exactly how you should do this. There's quite a few intricate details, but I will not talk about that. So where do you encounter these? So once you've identified this kind of structures, you start seeing them pretty much everywhere. So this is a very incomplete list, but just to give you an idea, if you do post-Newtonian corrections in GR, obviously the words suggest you start with a Newtonian description of gravity, and then you add corrections to it to get better and better approximations of GR. So this starts with Newton-Cartan geometry, and then you will get corrections to this kind of geometry. I will explain in more detail later what that looks like. As I already mentioned, if you have some space-time, the dissolution of Einstein's theory, but you go to infinity, typically you will get a non-Lorentzian geometry at the boundary. So examples where we know this happens are flat space, Lifshitz space-time, Schrödinger space-times. Schrödinger spacetimes were introduced by Son in the context of holography. And if you go to infinity, then you will find some non-Lorentzian geometry there. In fact, this is how I first encountered Newton-Cartan type geometries, because I was studying Lifshitz spacetimes, and it turned out that on the boundary of these spaces, you had to come to terms with the fact that they were not Lorentzian. Null hypersurfaces, for example, a black hole horizon, any null hypersurface is always a Coronian geometry. So future null infinity, null horizons, you get Carroll. These are the BKL singularities. So for example, the singularity near the Schwarzschild black hole. It turns out that the spacetime close to these singularities are also described by something called Carroll geometry. So in fact, if you take the Schwarzschild solution, then you will find Carroll geometry at the singularity, at the horizon, and at infinity. So it is really quite omnipresent in that sense. Condensed matter physics, typically systems are not Lorentz invariant. So if you want to use geometry to study the field theories involved, then you'll have to put them in a non-Lorentzian spacetime. Of course, the same with fluid dynamics. If you can study fluid dynamics on a curved background, you actually know quite a lot about the theory, because it's non-trivial for the theory to be well-defined on a curved background. And so a lot of people use that technology. Even if the ultimate application is in flat space, it's very constraining for the theory to be well defined on a curved background. For example, for there to be positive entropy production and all that. So if you want to study fluids that do not have any Lorentz symmetry, that are like Galilean invariant or that have no boost invariance, so boost agnostic fluids we call them sometimes, then you need to use these kinds of geometries. There are other instances where you find non-Lorentzian geometry, but I will not talk about this, just for completeness sake. Now, for the purpose of this talk, I want to study the non-relativistic expansion of GR in a covariant way. And the way we do that is by expanding it in powers of 1 over c. So you might be familiar with the expansion of GR in powers of g Newton. So this is like linearized gravity with respect to a certain like Minkowski space or ADS space, and then you can do an expansion in g Newton. But you can actually also expand it in powers of c, and I will talk a bit about how you do that. And this leads to a notion of gravity that we call non-relativistic gravity that is actually more general, quite a bit more general, than Newtonian gravity. And again, we'll see later exactly how. And that's the theory that I have in mind when I want to study fluid gravity. So I want to use that particular theory to see if there is like a non-relativistic ADS vacuum and some kind of boundary geometry on which you can define a non-relativistic fluid. So ADS CFT is very useful if you want to study relativistic conformal fluids. But if you want to study non-relativistic fluids, you have to change something. Now, people have worked on this. They introduced things like Lipschitz spacetimes, Schrödinger spacetimes, but because these are spacetimes whose isometry algebra is a non-relativistic algebra, so you can expect that the dual theory inherits that non-relativistic symmetry, which is in fact true. But it's still a solution of GR, and if you want to have a framework where you can study fluids or other systems that are non-relativistic generically, you may also want the bulk theory to be some non-relativistic theory. So that's kind of what we're exploring here. Okay, so when you do a 1 over c expansion of GR, I mean, some of this is textbook, some of the first calculations you do with Einstein's theory, and then normally you also make a weak field approximation. But you don't, that's actually an extra assumption that is completely independent of the 1 over c expansion. And so there is actually a way of doing this without assuming weak fields. And we call that strong non-relativistic gravity. And that is actually a theory that I will be using today. Now, you can ask if there's, we know about post-Newtonian corrections to GR, but that if you look at the details of that, this is very powerful if you want to compute, for example, black hole mergers in the regime where the system behaves non-relativistically, and you can compute radiation at infinity. So it's a very powerful and important method, but it's also quite messy. Pardon me for saying this. And it's not very covariant the way it's been set up. It's usually done in a particular gauge known as the harmonic gauge. And so we're looking for a more universal method that allows us to do non-relativistic approximations of GR coupled to some matter system where you want to be as general as possible. Other applications of this would be to study, say, quantum systems in non-relativistic but non-trivial backgrounds. So you can ask, what happens to quantum mechanics if I have a non-trivial gravitational background, like a Schwarzschild black hole or a Kerr black hole. So that's also quite interesting. So in fact, we've used this 1 over c expansion to find a new approach to study radiating systems in GR, but I will not be talking about this now. Another motivation, which is maybe more of a high energy motivation, is to ask questions about quantum gravity. Now, this is called the Bronstein cube. So you have 3 axes here. This is the axis where you turn on g Newton. This is 1 over speed of light. This is h bar. So this corner would be classical mechanics, and then you can go to special relativity, general relativity, quantum field theory, etc. So the holy grail would be to understand this corner here, where all of these constants of nature are order 1. And of course, it's obviously a very hard problem. But there is also this corner here, which is non-relativistic quantum gravity. And you may wonder what kind of theory sits there, if any theory at all. And so what do we mean by this? And I think that is actually quite a interesting and very non-studied corner of this whole Bronstein cube. Because imagine that there is I mean, this could be string theory or some other field of quantum gravity. If it's a, if you take a sufficiently careful 1 over c expansion, you should be able to go down this way and then land on this one. But if you reverse that logic, that means that something must live here. And then maybe I can start thinking about, if I know what that is, I can start thinking about 1 over c corrections and then start to study this one. So I think this idea may actually allow us to study quantum gravity from a different perspective and maybe learn a lot about this. So this is one of the motivations why people study non-relativistic string theory, because that could be one particular incarnation of that particular corner. Furthermore, we know that there are dualities between quantum field theories and string theories. Famously, the ADS-CFT correspondence is one of them. But you can ask whether that ADS-CFT correspondence is, whether that only happens in the relativistic domain, or whether this correspondence remains true if I start expanding in 1 over c. And we have quite a lot of circumstantial evidence to suggest that actually the correspondence survives that non-relativistic procedure in one way or another. So if you believe in the ADS-CFT correspondence, then a consequence of that is what we call fluid gravity, which is the long wavelength regime of the ADS-CFT duality. So the question, it's a very obvious question now to ask, is there something like fluid gravity for non-relativistic gravity? And that's more or less what we're going to talk about. So just to introduce fluid gravity to you. So in a nutshell, so this has been, so a lot of people have sort of contributed to this. So Son and Starinas, Cofton, Polycostra, and then these people in 2007. And so this is more or less the formalism that I will adopt. So the idea is that you take simply Einstein gravity with just a negative cosmological constant. This is the simplest setting in which you can do these things. And then you look for a solution that is known as an ADS black brane. So this is it's like a black hole, except the horizon has planar topology. So so this is the ADS black brane solution, which has been boosted. So it has a non-vanishing velocity. So this is like if this is in 5 dimensions, this will be your 4 velocity, which is defined here. So this is a Lorentz contraction factor, speed of light, and this is the velocity of the fluid. And this is the blackening factor, so there's some horizon radius here. And so the parameters of the solution are the horizon radius, which you can replace with temperature, and the velocity of the fluid. So this is an exact solution of the theory. But now what you do is that you say, okay, in order for this to be a fluid, I want these to be functions of the boundary coordinates. So I'm going to make them slowly varying functions of the boundary coordinates so that I can do a derivative expansion. And then you start solving the Einstein equations in a derivative expansion. And then you find that the Einstein equations will become equivalent to boundary fluid dynamics for the temperature and the velocity. And that's exactly how the fluid gravity correspondence works. Okay, so the idea of the talk will now be that we're going to study in some detail the 1 over c expansion of GR. I will then define what we mean by non-relativistic gravity, and then I will say something about fluid gravity and conclude with some outlook. Okay, so how do we 1 over c expand GR? So the first question is, in that field, where is the speed of light actually appearing? And for that, we need to change the variables of the theory. It's normally written in terms of the Lorentzian metric. But if you think a little bit about this Lorentzian metric, like I told you already that non-Lorentzian geometries are well described by Vielbeiner. So we expect non-Lorentzian geometry if we 1 over c expand GR. So a good thing to do is to start by reformulating GR in terms of Vielbeiner. But because of rotation symmetry, we're not going to use the spatial Vielbeiner. We're just going to lump them all together in this quantity called pi mu nu. So this is a Vielbein decomposition of the metric. T is the time-like Vielbein. There's a constant c. This is the speed of light. So this is like a tangent space speed of light. So if you have light goes in tangent space here, this is the time direction. These are all the spatial directions. Then this angle here is 1 over c. So as you take c large, you see that the light cones, they flatten out and you get Galilean relativity. And so these variables t and pi will be the variables in which we're going to write the theory. And keep in mind that pi has this signature because we've isolated the timeline field binder. Yeah, go ahead.
I think I just missed it. Can you explain again why you're not writing pi mu nu as e mu e nu?
You could if you wanted to, but because we're going to insist there is rotation symmetries, you have local rotation symmetry that forces these field binder to always lump together in pi. So this is the only rotation invariant combination. So you might as well just use pi. Yeah, okay. Right, so this is just a reformulation of GR, but we haven't really done anything. But the important step and assumption is that these variables now, t and pi, admit Taylor expansions in 1 over c. This is a non-trivial assumption. It's covariant, but there are coordinate systems in which this assumption is violated. It's not always true. That also means that, and I'll talk about this on the next slide, that once you are in a coordinate system where this is true, you're only allowed to do coordinate transformations that respect this property. So that will have important consequences. So it's possible that spacetimes that are diffeomorphic before you 1 over c expand are no longer diffeomorphic after you 1 over c expand. So one example of this would be Minkowski space in standard inertial coordinates or Minkowski space in Windler coordinates. They are diffeomorphic, but once you 1 over c expand, they are no longer diffeomorphic. They are really inequivalent spacetimes. Another assumption, which is really one of simplicity, and there's nothing particularly important, is that I'm only using even powers. You should, in general, also include odd powers if you want to study radiating systems, like production of gravitational waves. Then you have retardation effects, and retardation is captured by the odd powers in 1 over c. But we will not be needing that for our purposes, so I'll leave them out for simplicity. So what happens is that at every order in 1 over c, you introduce a new field. So the leading order fields are called tau and h mu nu, and these are going to describe our Newton-Cartan geometry. And then these subleading fields, n, b, and phi, they are going to be interpreted as gauge fields on that Newton-Cartan geometry in a way that will make more manifest in a minute. So if you do this expansion and in terms of the metric, this is what happens. So the metric is degenerate at leading order because it's just tau tau, and then you get an order 1 correction and then a 1 over c squared correction, etc., etc. So, like I said, when you start expanding the metric, basically you have to expand now everything. So you have to, so if you have diffeomorphisms that are generated by capital Xi, so the metric transforms with the Lie derivative along Xi, you are now, in order to respect the ansatz that I made that the expansion is Taylor in 1 over c, that means that all coordinate systems that are compatible with this also have to be Taylor expandable 1 over c, and that means that this generator needs to be expandable in this way. So the little Xi is what now corresponds to the diffeomorphisms in our Newton-Cartan geometry. And the subleading transformations, the zetas, they become gauge transformations of these subleading fields that appear in the expansion, okay? So this is what will happen in general. So all these subleading fields become gauge fields with respect to the subleading diffeomorphisms, which no longer have the interpretation of diffeomorphisms, okay? The diffeomorphisms of the Newton-Cartan geometry are really described by the Xi's, not by the zetas. Furthermore, this split between the t and the pi's, I mean, this was a Vierbein split, so this is also not, this suffers from an ambiguity, namely that I can do a local Lorentz transformation to go from t to t prime and pi to pi prime such that g remains the same. So there are local Lorentz transformations that mix them, and they also need to be expanded, and they lead to local Galilean transformations, and they're subleading corrections, okay? So there will be 2 types of gauge transformations. The diffeomorphisms and their subleading counterparts, and local Galilean transformations and their subleading corrections. Right. So this is the geometrical picture that you have to keep in mind. So just to give you an example of what, yes.
So, yes, that's right. So, are we going to view the diffeomorphism invariant as a global symmetry here?
It's still a local symmetry. So these are all local functions of space-time.
So when I say global, it's comparing to gauge redundancy. So it's a kind of
so
not a they are not gauge redundancy, right? I mean, for the leading order of the infinite.
So this psi is a diffeomorphism on our leading order geometry. So this is really a redundancy of the formalism, like you to have exactly like in GR.
Okay, thank you.
Yeah, nothing has changed from that point of view. Thank you.
So I have a question. So in this case, because you expand like everything in the 1 over C.
Yeah.
So when you do the deep transformation, do you need to also truncate, or it's going to be close?
Right. So if you look at this expansion, so for example, what you do is you act with a Lie derivative on this object, where the Lie derivative is with respect to capital psi, and then you ask, you then expand that, and then you match that with transformations of the subleading fields. So basically, that means that this will only transform under the Lie derivative of Lotto psi, so leading order diffeos. This one will transform under now two transformations. It will transform under the diffeomorphisms of the Newton-Cartan geometry, but it now also transforms under the subleading ones, the zetas. And the same for B and the same for all the other ones. But you can always truncate this expansion at any order that you like. So it's always consistent to truncate the expansion. Okay, any other questions? All right. So to give you an example of what these expansions do to a geometry, and also to highlight the difference between what we call the weak expansion and the strong expansion, let me just give you the example of Schwarzschild and ADS and de Sitter. So let's first do the standard, this is kind of textbook. So it's a weak non-relativistic expansion. So we write Schwarzschild, we reintroduce all the constants of nature, so G and C. And then if you treat the mass as independent of speed of light, and then you just read off what the expansion is and you match with the fields that we defined on the previous slides, then you get this. So you see that you get a Newton-Cartan geometry with absolute time. This is just a flat geometry in spherical coordinates, and you get a Newtonian potential, just as standard textbook stuff. So you see that also this M field, the time component of it gives you Newton's potential. That will actually be important, and that's always true in general. Now you can also take ADS or de Sitter, depending on, so the plus sign is ADS. And then there's a length scale here, but I can rewrite that in terms of like a Hubble constant. So I can say C over H, where H is independent of C. And I can again do an expansion in 1 over C, and then you get this answer here. So we get the same flat leading order geometry, but now the Newtonian potential is like a harmonic oscillator, which is really what ADS and DS are like from the point of view of Newtonian mechanics. So you either have an attractive harmonic oscillator or one that repels. Okay, now what happens if you take one of these strong limits? So let's go back to Schwarzschild and write it in terms of the Schwarzschild radius. And then that is just an integration constant. If I solve Einstein's equation, so Schwarzschild radius is an integration constant, I can assume that it doesn't depend on C. So if you do that, then and you expand in 1 over C, then you get a very different answer. You see, you get now the clock form is non-trivial. There's this blackening factor here, and the leading order geometry is curved. And the 1 over C expansion actually terminates after 1 order. Oh, I'm going a lot slower than. Thank you. So you see that these gauge fields are now 0. So this is what we call strong non-relativistic gravity. This is not captured by Newtonian gravity, but it is a solution of this non-relativistic gravity theory. And this is potentially a very useful alternative starting point to do approximations of GR. Like imagine you do post-Newtonian corrections, then in post-Newtonian theory, you start with flat space, then you add the Newtonian correction and then the post-Newtonian corrections. from this point of view, you would start with this solution and then start adding corrections to whatever system you're studying, which might be, this is still a work in progress, but it might be an interesting alternative. Right. Perhaps interesting to mention that you can work out the geodesics on this space, and they are on the nose identical to the geodesics you find in textbooks for the geodesics in the spatial geometry. So actually, this particular theory of non-relativistic gravity passes all the sort of tests of sort of solar system GR tests. They all are captured by this particular non-relativistic geometry. And if you think about it, there's nothing particularly relativistic about most of these tests. Like perihelion precession is not a relativistic effect. It's gravitational time dilation. And non-relativistic gravity captures gravitational time dilation. That was a question.
Yeah, I was wondering whether that thing is like some kind of a non-relativistic black hole or something.
Yeah, very good. I don't think so. And I can elaborate on that more in the break. But basically, this is actually something that probably will come back later, because I believe that these theories allow for finite temperature states, but they are not to be thought of as black holes. That's my short answer to this question. So there doesn't seem to be some kind of continuation beyond where this goes to zero. Like the trick that you do with Eddington-Finkelstein coordinates doesn't work here. So, I don't have a like mathematical proof that they don't exist, but I wouldn't expect them to exist. Well, yeah, that's also a bit of a hairy topic, because you need to find a curvature that is invariant under all the Newton-Cartan gauge transformations. But yeah, it would be. The ones that you can write down, they are finite. Okay, I think I have to speed up a little bit. So, okay, so what is this theory of non-relativistic gravity? So we'll have to expand the Einstein-Hilbert action. Now, the Einstein-Hilbert action, if you write it in second order theory language, then there's a Levi-Civita connection and all that. It turns out that if you expand the Levi-Civita connection in 1 over C, you don't get a very good connection on the Newton-Cartan geometry. And from Newton-Cartan theory, we know that there's a different kind of connection that we like to use. So that kind of motivated us to redefine or reformulate, rather, GR in terms of a different connection. These connections are dependent connections, so you can pick anyone you like. It's a question of convenience. So we're going to work with this particular connection. This is a torsion Voul connection. Now, you may think this is a weird thing to do, but the reason we use this is because once you start expanding, the leading order contribution from the expansion of this object is the connection of Newton-Cartan geometry. So that's the reason we use this one. It has a number of properties you can see here, but never mind the details. What happens is that if you now write the Einstein-Hilbert action in terms of this connection and these variables, you get this much longer answer. And you see that it starts at order C to the 6th, then there's this term, then at C to the 4th, you get spatial curvature, that's essentially what this is, and this is basically, at order C squared, you basically get this is the time derivative of pi that is basically like extrinsic curvature. If you're familiar with the ADM formulation of GR, then in ADM, T would be hypersurface orthogonal, so this term would be gone. Then you just have this, and then it's exactly the same thing as this is a slightly more general version of the ADM description of GR. Now we can expand this using this Taylor expansion, and then you just get a cascade of Lagrangians. And the way this works is that so there's a leading order theory, and next to leading order theory, etc. And you can show very generally that the equations of motion of the leading order theory are captured by the equations of motion of the next to leading order theory with respect to the new fields that you have introduced at that order. And the next to leading order theory reproduces all the equations of motion of the leading and next to leading order theory plus new ones. So it really is a better and better approximation as you go along. And you can show very generally that you can always truncate this expansion. It's a consistent thing to do, to always stop at the order that you want to. So here I just wrote down what these actions look like, but the details are not too important. Also, then you can show that Newtonian gravity comes from this particular theory. So if you set the cosmological constant equal to 0, and you couple this to a massive particle, then you can show that you get exactly Newtonian gravity in a covariant language. So this is the theory that is going to define for us non-relativistic gravity. So you don't always get Newtonian gravity. It depends on what matter you couple to that theory. So if you couple it to a massive particle, it leads to Newtonian gravity. But if you couple it to other kinds of matter, you can get more general solutions. Like if you, for example, if you add a cosmological constant, you get more general solutions. So in fact, so if you take that theory and you add a negative cosmological constant, you can show that it admits the following solution. This is what we call non-relativistic ADS. So the clock one form is now not exact, so you don't have absolute time. So this is so there is some kind of gravitational time dilation here. And then you have this. It looks very much like ADS in Poincare coordinates. And this is the vacuum. So these other gauge fields are now are set to 0. And you can ask what are the symmetries of this vacuum. So you solve these Killing equations, and you get exactly. So this is the lee derivative along the Killing vector has to be 0 up to a local gauge transformation, and this is a local Galilean boost. H has a gauge transformation acting on it that is exactly this. So this is the right equation to impose. And if you solve these equations, you get something called the Galilean conformal algebra. And that is exactly what you get if you take the relativistic conformal algebra and you send speed of light to infinity. Thank you. Now, you can show that when R goes to 0, then this blows up, and you can show that this admits a boundary in the Penrose sense that we know from ADS CFT. So very formally, you can think of the spacetime as now being the interior of some other spacetime bar that has a boundary. And then there is something called a defining function that has the property that is positive on M and 0 on the boundary. And also its derivative is non-vanishing on the boundary. And then you can rescale your metric variables in this way, and then you can extend them to the manifold with the boundary. And this allows you to define a boundary geometry on the boundary. And it turns out that because this omega function is defined up to rescaling it with an arbitrary positive function, this leads to a conformal class of Newton-Cartan geometries on the boundary. So at R is 0, we have a Penrose-like boundary with a Newton-Cartan geometry on that boundary. Okay. So we have a Newton-Cartan vacuum with a Newton-Cartan boundary. So now we want to do the same as in fluid gravity. We want to construct an ADS black brane, although the word black brane should be replaced with some other adjectives. So we want to construct an excitation, so that this means turns on M and phi, that respect time and space translations as well as rotation symmetries, because I want to respect these symmetries when I do the fluid description. And then you can show that by playing around with the gauge transformations of these fields and imposing that it has these symmetries, you can show that, and then solve the equations, you can show that the only solution that you have is this in a particular gauge is this one here, where A is some constant. So you turn on a Newtonian potential on this non-relativistic ADS space. And then you can do some kind of Pfefferman-Graham-like coordinate change, and then you can expand near the boundary. And then you still have to give it velocity, so now you have to boost it. But in this case, the boost is a Galilean boost. So you send x to x plus velocity times time. And then after doing some compensating Newton-Cartan gauge transformations, you can put the solution in this form here. So this boost is an asymptotic Killing factor. So the boundary, so the vacuum hasn't changed. Also, the M field hasn't changed, but everything that depends on velocity is inside phi mu nu. So here you have velocity-dependent terms here. And you can go through the whole song and dance of holographic renormalization, but to cut a long story short, if you now ask what is the boundary stress tensor, then you get this particular answer here. So M is a parameter of the solution, which you should think of as energy. So you have, so this is your energy density. This is the flux of the energy density. The momentum is 0. That's very unusual. I'll come back to this. And you have some stress. So there's a pressure here that has the right, I mean, it's 1/3 of the energy that is fixed by scale symmetry. And this is what we call a massless Galilean fluid. Now, normal fluids, the ones that we're familiar with, are massive Galilean fluids. And so the fact that you may wonder, was it a surprise that this is what we get? And the answer is no, it isn't a surprise, because if you start with a relativistic energy momentum tensor for a fluid, then the large speed of light expansion of that depends very much on the equation of state. And in order to get a massive Galilean fluid, what you need to do is you need to split off a rest energy, and then, so a rest mass, so mc squared, and then the internal energy of the non-relativistic fluid is at the next order. So this is what you need in order to get a non-relativistic fluid. But the equation of state for a conformal fluid says that energy is proportional to pressure, but pressure starts at order 1. So these two statements are incompatible. So you can never get a Bachmann fluid or massive Galilean fluid from this kind of procedure. So that's my last slide. So you can now ask, can we do better than this? Can we get a massive Galilean fluid? So I think what I've shown to you is kind of a proof of principle that non-relativistic gravity is rich enough to give you a non-relativistic fluid on the boundary, and that it in fact has all the right geometrical properties like non-relativistic ADS. So, but now we have to do a bit better. So we want to get some kind of scale invariant massive Galilean fluid, so that should have Schrödinger symmetries. And there is in fact a non-relativistic sort of solution. So it's some kind of Newton-Cartan space that has exactly Schrödinger symmetries, as we found in this paper. And it's given here. So I think what you should do is add a bit of matter to the theory, and such that this becomes a solution, and then repeat the whole process. Okay? And this is not unrelated to what Sun did back in 2008, but this will be the non-relativistic incarnation of that from the bulk point of view. And then the next thing will be to make M the energy and the velocity local, and we'll repeat the whole fluid gravity approach. I think I've now run out of time, so I'll leave the other comments for you to read. So thank you very much.
So when you were showing like the limits of, I think it was ADS and DS, can you go back to that slide? Like
Sure.
the relativistic, so that you got like after the
This one?
limit. No, it was more. It was, yeah, no. You have to go.
This is the first slide.
When you, I mean, it's when you show like that you got kind of this harmonic potential in the.
Okay, sorry.
after the
Yeah,
limit.
okay. Here.
Yeah, exactly. I guess there. So you start with ADS, you're getting that. So can you, so is it possible to get the symmetries of this like space-time you're generating from some contraction of like the conformal group or something like that?
Yeah, this would have what is known as Newton-Hooke symmetries. You can get it from, yeah, so you can start with the symmetries of ADS, and then you can 1 over C expand those or take contractions of that.
Okay, so
And then you would
from
get these
ADS you can
symmetries.
go to Newton-Hooke.
But just maybe now that you bring this up, it's good to highlight maybe that this is not the non-relativistic ADS that I mentioned later. That would be, in that case,
No,
because here I assume that the radius of ADS is proportional to C, and in the other case you would say it's C independent, so you get a different answer.
Okay, so that one is a kind of a strong
Exactly.
limit that
Exactly.
we're referring.
Yes.
Okay, thanks.
Just a short question. So the action, is it restrictive to do a 1 over C expansion compared to doing intrinsically Newton-Cartan geometry? For example, are there like effective field theory like, are you missing some of possible solutions or something like this because you're restricted to doing it from the C expansion way rather than doing just most general action to some extent?
Right. Okay. Yeah, good question. So I think that from the gravity point of view, it's not restrictive because the answer is you can show the answer is unique. Whatever action you get, you would have gotten it from intrinsic arguments as well. But it's more relevant for the matter sector. So the matter that you add to it is you can require that this is a 1/c expansion of relativistic matter, but you can also not do that. And then you can have more options. Yeah, definitely.
You mentioned that Newtonian gravity is obtained from the next to leading order term in the action. What are the equation of motion of the leading and the next to leading order?
Okay. So yeah, this is terminology that we introduced back in the day when we were doing this. But I actually think that the leading order theory should be really thought of. It's probably better to call this leading order and to call this some kind of action for constraints only, because this leading order theory, the only equation you get from this is that power must be hypersurface orthogonal. That's all it tells you. So it's kind of like a constraint. And then the first non-trivial theory is this one. And here the equations of motion are determining the spatial geometry of your, so you get equations for H rather. Very good. So you can, on very general grounds, you can argue that matter will never contribute to this because it starts at c to the sixth, which is, yeah, so the leading order theory starts at c to the sixth. That's too divergent for normal matter. The next leading order theory starts at c to the fourth. That is possible to source with matter. And in fact, this is also what the matter is actually what guides between the weak and the strong limit. So depending on when the matter appears for the first time, that will tell you whether your approximation is a weak field approximation or a strong field approximation. So in normal Newtonian physics, matter appears for the first time at this order. So this would be unsourced. And that tells you that, and this matter, which for example, here you have this one here, that will force the time to be absolute. But if you take different matter, then you can source this one. Like for example, cosmological constant is a trivial example of this. And then you can get strong gravity.